Okay, hello, welcome back. I made a video a couple of years ago of me doing most of this hyperbola packet. In a perfect world, where we had 90 minutes, usually 90 minutes isn't even enough, to introduce hyperbolas, give the definition of hyperbolas, explore, come up with different kinds of understandings about the basics, do the vocabulary, do the derivation of the equation in general form, and then we need an hour of practice. So I did much of this practice in a video which I'm about to send you, but then some of it I didn't do. So let's just keep going and kind of finish the packets, because there are 3 more problems. And one of the problems was on the bottom of page 5, though I might rewrite this packet slightly so the page numbers might not be accurate. But anyway, this was the problem. We have a hyperbola centered at the origin, and the lattice rectum runs from 9 15/2 to 9 -15/2. Sort of find everything. So, graph it, find the equation, the eccentricity, sort of everything. Okay, well, let's make a big picture first of all. What is this picture going to look like? Well, way out here at 9 must be the focus. So I have this kind of focus here at 9, 0. And then 15/2, so that's like 7.5 or something. 9, 15/2. And way down here, we have 9, -15/2. This is the lattice rectum. So that's a chord through the focus perpendicular to the line through the foci. And, okay, well, how can we find out everything there is to know about this hyperbola? Well, first of all, you just have to know some things. Now, I know I did this in the other video, but I'll just kind of do it again really fast or something. I need to know what these points are. So if I have a generic, maybe it's not necessary to do this again, but okay, here we go. If you have this generic hyperbola where this is A, 0, and this is C, 0, then let's just find, once again, the length of the lattice rectum. And so what we're going to do is construct, I'll do it here in blue, this segment. And what do I know about this segment? It's perpendicular to the x-axis, and it passes through the focus. So that means this coordinate up here must be C, something. Let's call it, I don't know, let's call it like L for lattice rectum. Okay, and so if that's the case, then it means that this segment has length L and this segment also has length L. And what I want is a general formula for the length of the lattice rectum in terms of the rest of the properties of the hyperbola. Okay, well, we can do it by simply using the fact that the point C, L must be on the equation. And so if I start with a generic horizontal hyperbola, okay, the other half that's going to be over here, a generic horizontal hyperbola is going to have equation, well, x has been stretched out by a factor of a, and y has been stretched out by a factor of b. And so a generic horizontal hyperbola centered at the origin is going to have this equation. Okay, and now, since that's true, let me plug in my point C, L, and see what I can find out. Well, if I plug in C for x and L for y, I get C squared over A squared minus L squared over B squared equals 1. So now I'm just going to solve for L, and that'll be that. Okay, so moving that over and moving that over, I get C squared minus A squared over A squared equals L squared over B squared. Okay, I kind of did a couple things at once there, I guess, but maybe that's not so hard to see. Subtract 1 and get a common denominator. And now C squared minus A squared just is B squared. So I really do get L squared over B squared equals B squared over A squared. And so, what is L squared? It's B to the 4th over A squared, and so L is B squared over A. Okay, so this is a little bit of background knowledge. We derived this in the ellipse packet, page 7, not live in class, but you looked at it. I did it in one of these videos, and I just did it, again. So, okay, knowing this fact, it means that this is now basically kind of like an algebra problem, right? If I know that my center is at the origin and that the lattice rectum runs from 9 15/2 to 9 negative 15/2, then I know two things. I know, first of all, that C is 9, and then I also know that B squared over A is 9/2. Or sorry, is 15/2. And I also know that the relationship between A, B, and C. I pretty much just defined B squared to be C squared minus A squared. In other words, we also know that A squared plus B squared equals C squared in a hyperbola. And so this is all really just to get you kind of comfortable with all of these facts by just doing some math problems. This basically just boils down to, can you solve this system of equations? And it's a system of two equations and two variables, so it should be solvable. How are we going to do it? Well, I guess the thing to do is to simplify this kind of somehow. This is telling me, this first line is telling me that B squared equals 15A over 2, and so it seems that the simplest thing to do is to, so I just kind of cross multiplied here. If I just stick this in to there, then that is seemingly going to do the job. So now I have, following the method of substitution, I get that B squared is 15/2 A equals 81. Now I just have a single quadratic equation to solve in one variable. Let's multiply through by 2 to get rid of the fractions. So that's 2A squared plus 15A, 162, so that's minus 162. That's a bigger number than I was expecting, but I guess that's just right. What is 162? This is 81 times 2, and then that's just like a bunch of 3's. So, cha-cha-cha-cha-cha. When it comes to writing the factor pairs of 162, I guess I have 81 and 2. I have 3 and 54. I have 6 and 27. No. I have 9 and something. 18. I have, is that it? Yeah, that might be it. 2 and 27. Yeah, I think I'm done. Well, is that true? 3, 4. That's probably right. Okay, and then this is 2, 1. All right, so I need to find differences which add to 15. Differences which add to 15. Wait, 18 and 9. Is that even right? 6, 9, 18, 9. Yeah, that is right. Okay, differences which add to 15. Wait, what am I doing? A squared plus B squared equals C squared. C is 9, 81. This is seemingly all correct. This is seemingly correct. 162. Alright, so I just need to do it, I guess. Differences of 15. Oh yeah, there it is. 12 and 27. Okay, so that wasn't so bad. I just psyched myself out for a minute. But the bottom line is, this factors as 2A27, A6. And what do I get? 2A squared minus 12A plus 27A minus 162. Okay, so since A has to be positive, then this tells me that A is 6, and now I'm on my way to being done with this problem. Because once A is 6, then I guess I can just find B, right? Because what's B, or rather, what's B squared? If A is 36, then B squared is going to be 81 minus 36, which is like something. 45. I think B squared is 45, because 45 and 36 is 81. Yep. And if A is 6 and B squared is 45, then what's C squared? Oh, I already know that C is 9, so I guess I'm just checking that. So C, so that was not important. Okay, well, once I have A and B, then I am pretty much done, because what is then the equation of this thing? Well, it's going to be a horizontal hyperbola, so it's going to be x squared over, I'm being stretched out in the x direction by 6, so that's 36, minus, and I'm being stretched out in the y direction by, you know, root 45. So, okay, I'll write that like that. And this is 1. Alright, so that's the equation of the hyperbola. And I'll go sort of down over here to negative 9, 0. What is the vertex is going to be here at 6, 0. And negative 6, 0. And now I would like to make my happy box. What are the dimensions of the happy box? Well, B is being stretched out by root 45, which is just 3 root 5. But sort of more to the point, I guess, root 45 is approximately, well, it's going to be a little bit less than 7. Let's call it 6.8. So this, in this case, the happy box is going to be up here like this. The width of the happy box is 12. The height of the happy box is 6 root 5. So anyway, the point of this is that I can draw my asymptotes. And then the hyperbola itself is going to pass through this latus rectum point and pass through these guys like that. Alright, so what's done? I found A, B, and C. I graphed the hyperbola. I can give the equations of the asymptote. Let's see, what's this asymptote? Well, this is like 6, and this is 3 root 5. So, it's going to be root 5 over 2. So, is the slope. So, y is root 5 over 2x, and no, I guess that's the negative one, and this is the positive one. Y equals positive root 5 over 2x. I guess I could check my answer key. Is this all just like right? Yep, it totally is. So I have my asymptotes. What's my eccentricity? My eccentricity is just defined to be C over A. So my eccentricity is C is 9, so that's just 3 halves. So I have my eccentricity, I have my equation, I have the equations of my asymptotes. What else is there to do? Maybe nothing. So I'm done. Alright, good. That was like a pretty hard problem. Let's do 2 more. The 2 more problems that we have both feature doing a bunch of algebra kind of first to find the equations of the things. So don't be scared of that. Okay, let's go. Page, second to last page. Here we go. 25x squared minus 9y squared minus 100x minus 72y minus 269 equals 0. Okay, you may or may not require, direct instruction on this topic, but since we didn't do problems like this on the ellipse packet in class because we ran out of time, and we didn't go over the ellipse homework live in class, it seems like something that we should do. So, how do we deal with this expression? Well, it's quadratic in 2 different variables, and because these 2 numbers have opposite sign, I can tell already that this is going to be a hyperbola. So, how are we going to make some sense of this hyperbola? Well, we need to put it in a form that we understand, and so the goal is collect all the x's together, collect all the y's together, and move everything else over to the other side. So let's do that right now. So I get 25x squared minus 100x, and then this is minus 9y squared minus 72y, and okay, and then this 269 kind of goes added to both sides. Move it over there. Okay, I'm going to do this nice and slow and careful and patient, and this is how you should do it too, such that you don't make any mistakes and everything is great. Okay, well, I need to complete the square in both variables. So I need to factor out 25, and when I factor out a 25 here, I get x squared minus 4x. Okay, great. And now here, I have to be very careful because I'm factoring out a negative 9. And if I factor out a negative 9, then I'm left with y squared plus 8y, because math, equals 269. Okay, and now we sort of can't go wrong, right? Because what's next? We need to complete the square. One number goes here, 4 of course, but by writing a 4 here, what I've really done to the left-hand side was to add 100 to the left-hand side. So if I add 100 to the left-hand side, then I have to add 100 to the right-hand side also. And how about now, this needs to be a 16, but by writing a 16 here, what have I really done? I really just subtracted 9 times 16, which is 144, from the left-hand side. So to balance out this algebraic operation of subtracting 144, I need to also subtract 144 from the right-hand side. Okay, so that's kind of easy, but sort of important. All right, so therefore, what do I end up with? 25x minus 2 squared minus 9y plus 4 squared equals, what's all this over here? Well, it's going to be 369 minus 144, and that will be 125? 225. 225. Let's see, is that true? I think it's just true. 369 minus 144 is 225. Yep. So, good. Finally, I should divide both sides by 225. And if I do that, I get x minus 2 squared over 9 minus y plus 4 squared over 25 equals 1. Okay, that was like the easy part. So this is just more or less mindless algebra. I mean, computers can do this, so can you. Just make sure you are careful about it. What have I accomplished? Well, I have now forced this algebraic equation to be in a form such that I can recognize and analyze what is going on. What is going on? Well, this is hyperbola. What kind of hyperbola is it? Well, it's an x squared minus y squared type hyperbola, so it's definitely going to be horizontal. What else do I notice? Well, I notice that the x-coordinate is being stretched out vertically by a factor of 3. So a is 3, and because that's what a means, it's the amount by which... Sorry, let me say that one more time. I don't even know what I just said, but I know I was doing this with my hands, which is wrong. X is being stretched out by a factor of 3. And so since it's a horizontal hyperbola, then the horizontal stretch is going to tell you how far apart the vertices are. And the answer is that the vertices are going to be 6 apart from each other because we're stretching out the hyperbola horizontally by a factor of 3. And B is going to be 5 because we are stretching out in the y direction by a factor of 5. Okay, and the other thing that we see is that the center of this hyperbola is not at the origin, but is in fact at the point 2 comma negative 4. Alright, so we have a horizontal hyperbola, center at 2 comma negative 4. Let's make a picture of this right now. So 2 comma negative 4 is my center. And what else? Well, A is 3, so I'm being stretched horizontally by a factor of 3. So let me skip to the right 3 and skip to the left 3. So there's a point and there is another point. That point is 5 comma negative 4, and that is negative 1 comma negative 4. And that is my transverse axis. This is the center. These are my 2 vertices. Okay, what else? Well, I also know that this hyperbola has been stretched vertically by a factor of 5. So counting up from the center, I go to this point which is kind of 5 up, or maybe I just go straight for the happy box. So what's the happy box? The happy box has been stretched vertically by a factor of 5, so up to y equals 1, and then down by 5, 2, 3, 4, 5. And okay, what have I just done? I've just made a rectangle centered at 2, -4, which is 10 high and 6 wide, owing to the fact that y has been stretched out by a factor of 5 and x has been stretched out by a factor of 3. Why make this box? Because the diagonals of this box are the asymptotes of my hyperbola. Okay, and well, great. Then what does the hyperbola look like? I can pretty much just draw it already. It's gonna look like that. And like that. Horizontal hyperbola, vertices at 5, -4, and -1, -4, and everything's looking good. I'll just check my stuff, but yeah, it's just all right. Okay, great. What's left to do? One thing I can do is I can give the equations of these asymptotes. Well, these lines have slope up 5/3. That's certainly true, because that's the dimensions of this box, right? Up 5/3. But it's not just y equals 5/3 x, because this line doesn't go through the origin. This line goes through 2, -4. Okay, so a little bit of like algebra 1 background knowledge is required, that if you want to write the equation of a line, you know the slope of the line, and you know a point that the line goes through, in this case 2, -4, then I can write this as y plus 4, comma, 5/3 x minus 2. That is just the equation of a line with slope 5/3 that goes through 2, -4. And then we can do the same thing here. This also goes through 2, -4, but now the slope is -5/3 x, so x minus 2. Okay, so I've written now the equations of the asymptotes for this hyperbola. What's left to do? Well, we should find out where the foci are. In any hyperbola, a squared plus b squared equals c squared, because we just defined b to be defined b such that b squared is c squared minus a squared. So, okay, what does that mean? It means that c in this case is going to be root 34, I guess. So this is root 34. So this is like, I don't know, 5.9 or something. So, where are my foci? They are root 34 away from the center. So I need to go 1, 2, 3, and then sort of over here-ish. I get one focus, and over here I get kind of like another one. And what are the coordinates of these foci? They're going to be go over 2, and then go over an additional root 34, and then down -4. Cha. And over here, it's like go over 2, and then back root 34, and then down -4. So, alright, I got my foci, I got the coordinates of my foci, I got the equations of my asymptotes. I think we're pretty much done. 2 more tiny things. What is the eccentricity? Eccentricity is c over a, so that's just going to be root 34 over 3. There's not much exciting to say about that. And then finally, what's up with this lattice rectum? Well, we've seen already this formula that L is b squared over a. And in this case, a is 3, so this L is like 25/3. So what does that mean? That means that my lattice rectum is up 25/3 and down 25/3 from the focus. So adding this to the picture now, 25/3 is like about 8 something. So okay, I have no axes, so I sort of can't be wrong. I have my one lattice rectum and my other lattice rectum. Picture not so great, but it's easy to write out what the equations are, or what the coordinates of these 4 points are. This one is going to be go over 2 plus root 34. Okay, I can't really squeeze this in, so I think I'll just write it over here, right? What do? We go 2 plus or minus root 34. In other words, either go over to 2 plus root 34, the right focus, and then go up and down, or go to the left to 2 minus root 34, and then go up or down. How much do we go up or down? Well, from negative 4, we go up or down 25 thirds. Okay, so this is just a very efficient way of writing that there are actually four points that I care about, and the 4 points are 2 plus root 34, comma, negative 4 plus 25 thirds. That's the point in the top right. Then there's 2 plus root 34, comma, negative 4 minus 25 thirds. That's the point in the bottom right. Then there's 2 minus root 34, comma, negative 4 plus 25 thirds. That's the red dot in the top left. And 2 minus root 34, comma, negative 4 minus 25 thirds. That's this point right here in the bottom left. Okay, so for in the future, I think we can just write it like this, as long as that's something that you understand. Okay, good. So this is just like all the problems we've done before, but maybe like a little bit harder. Let's do one more, and then that will be the end of this packet. Okay. Good. 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 Last problem. Negative 25x squared plus 4y squared minus 150x 16y is 309 equals 0. Okay, let's do it. Step 1, mindless algebra done very carefully. So we're going to collect the x's together. So that's negative 25x squared minus 150x, and then plus 4y squared minus 16y, and then I'm going to add the 309 over to the other side. Okay, great. Now let's complete the square. First, I shall factor out negative 25, so that's x squared. You really got to be careful about this kind of thing. Plus 6x, because 6 times 25 is 150, but if you factor out negative 25, then that becomes positive 6. Here I'll factor out a 4. I'm left with y squared minus 4y, and this is my very organized way of doing this. You could even skip to the next line or something, and but I'll just use a different color now. Don't try to skip too many steps here. One number goes here. Well, this is plus 9, of course. And what did I just do to the left-hand side of this equation? I just subtracted 225. So minus 225. And yeah. And what number goes here? Well, 4. And so I just added 16 to the left-hand side of this equation, so I'm just going to add 16 to the right-hand side over here as well. Alright, so what does that give me? It gives me 325 minus 225, so it's going to be just 100 on the right. So this is minus 25 x plus 3 squared plus 4y minus 2 squared equals 100. And let's just put this in a different order. So it's really like 4y minus 2 squared minus 25x plus 3 squared equals 100. And finally, divide the right-hand side by 100, giving me y minus 2 squared over 25 equals, minus x plus 3 squared over 4 equals 1. Okay, looking good. Now what? Now I'm kind of just ready to begin this problem. What do I see? Well, this is hyperbola is in the form y squared minus x squared. So if this hyperbola is in the form y squared minus x squared, then this is going to be a vertical hyperbola. And I think I mentioned this in one of the other videos, but you can sort of think of like, y squared minus x squared equals 1 as kind of being sort of, it's a hyperbola, but it's kind of like the unit circle of hyperbolas. In fact, it's called the unit hyperbola. So if this small digression helps some of you, then that would be something worth doing. What can I say about this? So sort of sidebar over here. Let's just explore this y squared minus x squared equals 1, thing. And what do I know about this thing? Well, I can just attempt to graph it. And of course, it's just true that y squared is always x squared plus 1, which means that y squared is always going to be, y squared is always going to be more than 1. And if y squared is always going to be more than 1, it means that y is always going to be more than 1 or less than negative 1. And so you can kind of plug in some points or something. If you plug in, if x is 0, then y has to be either 1 or negative 1. And so you get this point 0, 1, and this point 0, negative 1. And what else can I say about this? Well, y is pretty much just like root x squared plus 1. And so as x goes to infinity, y is pretty much just looking like x. And if as x goes to infinity, y is pretty much just x, what that means is that y equals x is an asymptote. Asymptote. And that's just exactly true. We get this kind of line y equals x asymptote and y equals negative x also. And we already said that the curve has to have a y-coordinate which is either greater than 1 or less than negative 1. And so what you get, even if you sort of didn't know anything about hyperbolas, and you were just given this equation kind of out of the blue, what you end up with is something like this. And what you have here is the kind of most basic hyperbola in a kind of a sense. Here you have this happy box, and this happy box is a 2 by 2 square centered at the origin. And you go over 1, up 1 to get this line, which has slope 1 and all that kind of stuff. All right, so if this helps you, this is in fact called the unit hyperbola. And there's not just one unit hyperbola. Well, kind of like there is, but there's a vertical unit hyperbola, and then there is a horizontal unit hyperbola. So this kind of explains in some way, potentially, to some people, why, when it is of the form y squared minus x squared, why it's guaranteed to be vertical, right? Y is always going to be more than 1 or less than negative 1, and x can in fact just be anything. Right. So, good. Why do I care about that? Well, I don't really, but if I understand y squared minus x squared equals 1, then I can understand other hyperbolas. For example, what is there to say about y squared over 25 minus x squared over 4 equals 1? Well, this is going to just be that hyperbola, but with the y-coordinate stretched out by a factor of 5, and the x-coordinate stretched out by a factor of 2. Because, after all, this is just y over 5 squared minus x over 2 squared equals 1. So just like every ellipse can be thought of as a stretched out unit circle, every hyperbola can be thought of as a stretched out unit hyperbola. Hopefully this is helping some people, and therefore what will it look like? Well, up here at 0, 5 will be a vertex, down here at 0, negative 5 will be another vertex, and x equals 2 means that the happy box has been stretched out by a factor of 2. And so this will be like 2 over and 2 over that way, and so what we have is this 2 by 5 box, or rather the box is really like 10 by 4, 4 wide, 10 tall, and the hyperbola itself is going to look like this. Okay, if you made it to the end of this packet, you've probably already absorbed this message, but that's what's really going on. This is the kind of thinking that you need to then do this problem. Okay, well, what is this problem? Well, it's going to look exactly like that, right? It's going to be a vertical hyperbola, which has been stretched out by a factor of 5 vertically and stretched out by a factor of 2 horizontally, but the center is not going to be at the origin, but instead at -3, 2. Got to be kind of careful about that. All right, so let's just finish this problem now. I think there's nothing more to say. The center is -3, 2. A is 5 because the vertices are 5 away from the center. B is 2 because we've been stretched out horizontally by a factor of 2. C is going to be it's just going to be root 29. So it's going to be like, I don't know, whatever that is, 5.2 or something like that. 5.3 maybe. Who knows? Who cares? And I'm ready to just graph this thing. So let's graph it now. What's it gonna look like? Not happy with that, but too bad. Center -3, -3, 2. So that's -3, 2. Where are my vertices again? They're 5 up. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I made some bad choices here, but too late. Have I done this problem correctly? Yeah. So this center was -3, 2, but this is going to be, one vertex is going to be at -8, 2, and the other one, 1, 2, 3, 4, 5, will be down here at, sorry, what happened? -3, 2, this should be -3, 7, is what I meant to say, of course, and this will be at -3, -3. This is just like all right, yeah? Yeah, of course it is. Right, well, some of my work here is kind of getting in the way of my picture, but yeah, A is 5, B is 2, and I'm ready now to make my happy box. And for the happy box, I go over 2 and in all kind of directions, and then I make my diagonals, and those are going to be the asymptotes. So the hyperbola itself is going to look kind of like this and like that. Great. Pretty bad picture there, but I forgive myself. Okay, and now what's left? Where are the foci? The foci are going to be quite close to the vertices because A is 5, but C is only a little bit more than 5. So my focus is going to be here. That's going to be at -3, comma. Well, it's going to be root 29 away from the center. So 2 plus root 29. And the other focus will be down here. It's going to be at -3, comma, 2, comma, 2 minus root 29. Alright, and another thing we can do is to write the equations of these asymptotes. What about this one over here with positive slope? What's its equation? Well, it's just a line with slope up 5 over 2. So that's going to be, it's going to have slope 5 halves, but it's been moved, this line, so that it goes to the point -3, comma 2. So this is going to be y plus 2, no, minus 2 equals 5 halves x plus 3. So it's just the line y equals 5 halves x, but it's been shifted by -3, comma 2. And then this line here is going to be y minus 2 equals -5 halves x plus 3. Alright, what's left? I got my foci, I got my equations of asymptotes, I got foci, equations of asymptotes. I think I'm pretty much done. We need to find the endpoints of the latus rectum, but I don't really feel like doing that right now. The eccentricity is c over a, so that's root 29 over 5. So it's only a tiny bit more than 1. And then, yeah, the final thing to do is to note that b squared over a, in this case, is 25/4. So that's like 6.25. And it might look Wait a second. Yeah, 6.25? Sure, no, that's just wrong. 25/4. 4, that was just wrong. Totally wrong. B squared over A should be 4/5. So, yeah. And so, in fact, this is a very tiny, tiny little lattice rectum here. It's going to be 4/5 in either direction around this point. And so, agreeing to write this in the good way, the 4 endpoints of those two different segments have coordinates. I go over -3, then I go plus or minus 4/5 in either direction, comma, up and down by the y coordinate of the foci, which is 2 plus or minus root 29. And I think that's just all there is to say about that. Yeah. Good. And minus 15. What have I done? Minus 15 and 4. Yeah, minus 11, minus. Yep. Okay, so that completes the final problem of this packet. And hopefully you've watched all these videos and you're all caught up to date with hyperbolas and there's some homework to do. And I'll see you back in January.